Welcome to this video. In this video we will do ad hoc analysis of a circuit with a dependent source. The motivation for this circuit is an op-amp amplifier. Op-amps are differential voltage amplifiers with very high gains. They turn out to be extremely useful in all sorts of different circuit design problems. On the left here we have a circuit that shows an op-amp. The op-amp is this triangle guy here. And the idea is that the output voltage, the voltage at this point, is proportional, typically with a very large constant of proportionality, to the difference between the voltage at this input and the voltage at this input. This is called the non-inverting input, and this is called the inverting input. And with these op-amps and some the judicious use of resistors, you can come up with useful feedback combinations that make a lot of very useful circuits. So on the right, I've drawn a very simplified model of an op-amp. The stuff that's in dashed green lines is basically the things internal to the op-amp. And this is an extremely simplified model of an op-amp. Again, the purpose here is really not to cover all the things you need to know to do the analysis of an op-amp, but more to show you how to do the analysis of a circuit when you have a dependent voltage source. So in this case, the dependent voltage source looks at this voltage here, which I've labeled Vx, and the output of the voltage source is 1,000 times Vx. Now again, this is really the 10 k ohm resistor and the 1,000 times in the gain of the dependent voltage source. This really are the specifications for a crummy op-amp. This is not the sort of thing you would use in real life, but it makes a reasonably good numerical example. Okay, so how do we begin trying to analyze this op-amp? Analyze this circuit. Unlike many other circuits we've had, you can't start at one side and work your way through to the other using, say, equivalent resistances and so on. What we will have to do is we'll have to use an unknown, which in this case we'll call Vx because we've already got it defined in the circuit. And we'll have to use various analysis techniques to figure out what the output will be. Well, we'll have to come up with equations, an equation for Vx, solve it, and that will tell us what the output will be. So the first thing we notice is that the output Vout, that's the voltage from here to here, which is the same as the voltage across the dependent voltage source. So Vout is 1,000 times Vx. So if I can solve for Vx, then I will be able to I'll be able to solve for Vout. It'll be pretty easy. So then the question arises, how can I solve for Vx? Well, this is going to be sort of tricky. What I'm going to do is apply Kirchhoff's current law at this node. In fact, this is going to be tricky enough. We'll do a different color here. So I'm going to apply Kirchhoff's current law at this node. And you remember that Kirchhoff's current law says the sum of the voltage, or the sum of the currents entering a node is 0. Or the sum of the voltages or currents entering the node is equal to the currents leaving the node. So let me define a bunch of currents coming in. I'll call this I1, and I'll call this I2, and I'll call the current going down this way I3. So what I need to do is figure out what these currents are. And it turns out that if I knew what Vx was, I could figure out the voltage across each of the resistors. And from the voltage across each of the resistors, I could find the current. And from the current, or I could then use Kirchhoff's current law. Since I don't know what Vx is, I'll have to figure out what the voltage across the resistors are in terms of Vx. So let's start then with I1. The voltage across this 1 k ohm resistor, that is from here to here, I can find by noting that the voltage from here to here is 1 volt. And so I go from here to here plus the voltage from here to here, which is Vx, is equal to 1 volt. Or in other words, the voltage across this 1 k ohm resistor is 1 volt minus Vx over 1 k ohm. And again, I can see that, or I can see that this is the voltage, the 1 volt minus Vx, by noting that from here to here is 1 volt, from here to here is Vx, so from here to here has to be 1 volt minus Vx. Okay, so that gives me I1 in terms of Vx. Okay, let's see if we can now find I2. Okay, well, again, the way I can do this is I can see that the voltage from this point to this point is V out. The voltage from this point to this point is Vx. And so the voltage across this 2 k ohm resistor is V out minus Vx. So I can write this as V out minus Vx over 2 k ohms. But I know that V out is 1,000 times Vx. So I can write this as 1,000 Vx minus Vx over 2 k ohms. Okay, so far so good, hopefully. Now finally, to get I3, I know the voltage across this 10 k ohm resistor, it's Vx, and so I can just write Vx over 10 k ohms. Okay, so the idea here is I've computed the currents going into and out of this node. Now I can apply Kirchhoff's current law to say that the sum of the currents going in is equal to the current leaving. And before I do that, though, let me take this expression and simplify it one step further. I can write this as 999 Vx over 2 k ohms. Okay, that will make things easier. Now I can go back to this node and say that the sum of currents entering is equal to the sum of currents leaving. And so if I do that, I have I1 plus I2 is equal to I3. And now I can plug in the values that I computed for these guys. I1 is 1 volt minus Vx over 1 k ohm plus I2, which is 999 times Vx over 2 k ohms, is equal to I3, which is Vx over 10 k ohms. Okay, well, how do I solve this? It's clear now that this is in terms of only, I have an equation then that is in terms of only Vx, so I should be able to solve this for Vx, and from that I should be able to find V out. Well, let's do a little bit of rearranging before we just solve it. So we can say that Vx over 10 k ohms plus 999 Vx over 2k ohms minus Vx over 1k ohm is equal to minus 1 volt over 1k ohm. Okay, so I have just simplified. I basically have gotten all the terms that include Vx on one side and all the other terms on the other side. So now if I take this equation and multiply this side by 1k ohm and this side by 1k ohm, I will have Vx over 10 plus 900, whoops, let's do this in the proper color. We've been consistent, unusually so, for so long, plus 999 over 2 Vx minus Vx is equal to minus 1 volt. So now I factor out a Vx. 1/10 plus 999 over 2 minus 1 is equal to minus 1 volt. And from this, I can solve for Vx. And when I do, I get the following. Okay, so when I actually solve this for Vx using my handy calculator, I end up with Vx is equal to minus 0.002, and yeah, that's about well, that's about as many significant figures as I'll go out. Okay, and from that, V out is 1,000 times Vx, which is minus 2 volts. Okay, so to three significant figures, my output voltage is minus 2 volts for an input voltage of 1 volt. Now, if I go out to 6 or 7 significant figures, some other stuff shows up here, but since I'm too lazy to write it down, I won't. So basically, this shows us how we can solve a circuit that has a dependent source in it. In this case, it got very complicated because we had to solve for the currents through each of the resistors, and then we had to apply Kirchhoff's current law to get a relationship between those currents. And once we had the relationship between the currents and we knew how each current was expressed in terms of Vx, we could solve for the problem. What we've actually done here is a simple version of what's called nodal analysis, which will be the topic of subsequent videos. But this also does demonstrate one way to solve a circuit that has a dependent source. Again, in this case, because it was complicated, we had to leave Vx as a variable and then solve for it. So hopefully you found this useful, and we'll see you later.